In this lecture, we are going to discuss the differences between an electric vehicle and a hybrid electric vehicle. On the left-hand side of the slide, you have a table which has three columns. The first column represents the energy source, and you have three types of energy sources. You have the fossil fuels on the top, represented by gasoline or diesel fuels. We have electricity in the middle and hydrogen in the bottom. One observation I want to make is that in US we call gasoline engines or gasoline fuel, and in the United Kingdom we say petrol fuel or petrol engines, but they are the same thing, they use the same fuel. In the middle you have the different types of hybrid electric vehicles or vehicles, which can range from purely internal combustion engine vehicle, which use 100% fossil fuel and only internal combustion engines for propulsion. And in the bottom you have full electric vehicles, which use 100% electricity as energy source and 100% electric machines for propulsion. The fuel cell vehicle, it's also using the electric machine for propulsion, but as energy source it uses hydrogen. Now between the internal combustion engine at the top and the electric vehicle, we have a range of hybrid electric vehicles. The level of hybridization is also explained in the right table by the electric power available and also the CO2 saving potential. For example, an electric vehicle has an installed electrical power of about 60 to 120 kilowatts. Of course, it can go much higher to hundreds of kilowatts. And the saving potential is 100% compared to internal combustion engines on any DC cycle. 100% saving potential for CO2 means that there are no tailpipe emissions, and that's obvious because electric vehicles have no internal combustion engines. Now coming back to the level of hybridization, we have micro hybrid electric vehicles. These type of vehicles use internal combustion engine for propulsion, but they have a smart low voltage charging system. As you know, a normal internal combustion engine vehicle has an alternator, and the alternator generates electricity, which feeds into the low voltage system, 12-volt system, and also charges the low voltage battery. In the case of micro hybrids, that low voltage system is smart and has an alternator that can go in standby mode. And while the alternator is in standby mode, the low voltage battery will sustain the low voltage system. The benefit of micro hybrids is that putting the alternator in standby mode, you don't put load on the internal combustion engine, which means you use the fuel not to generate electricity, but to generate torque, which means you can have a CO2 saving potential of around 3 or 4% compared to a normal internal combustion engine vehicle. Micro hybrids also, they have a low electric power, less than 5 kilowatts, and this power is mainly the power generated by the alternator itself. The next type of hybrid electric vehicle is the MHEV, which stands for mild hybrid electric vehicle. In this case, we have an electric machine which can have the role of an alternator and also as a motor. Usually MHEV systems are 48 volt types of system, and the installed power for the electric machine is around 10 or 20 kilowatts. Increasing the level of electrical power will bring higher benefit in terms of CO2 potential. Also, in the middle column in this table, we can see for which vehicle segments these technologies are applicable. For 12-volt micro hybrids, usually the A and B vehicle segments are using this type of technology because it increases the efficiency of the powertrain for small vehicles. The 48-volt mild hybrids can be used for all types of vehicle segments, and they can also equip gasoline or diesel engines. What's specific about mild hybrids, and especially 48-volt ones, is that the electric machine can generate electricity, so you can recuperate energy during braking, and also you can generate torque during acceleration, so that is why you can have a higher benefit in terms of CO2 potential. The next type of hybrid is the HEV, which stands for hybrid electric vehicle. This type of hybrid is also called full hybrid or self-charging hybrid, because all the electrical energy going into the high voltage battery comes from energy recuperation or from the engine. So it does not have a plug-in capability, which means it cannot be charged from the grid. For a full hybrid, the installed electrical motor power is around 20 or 40 kilowatts and is usually suitable for vehicles in the C and D segment. Of course, having a higher electric power, you can have a higher CO2 saving potential, around 20-30%. In addition to the functions of an MHEV, which means energy recuperation and torque boosting, in the case of the full hybrid, having higher electrical power, you can also drive in electric mode. Usually, hybrid electric vehicles can drive into EV mode up to 5, 10, 15 kilometers per hour, so only low speeds. Moving down to PHEVs, which stand for plug-in hybrid electric vehicles, we have higher electric motor power and also higher CO2 saving potential. The main difference between a PHEV and a HEV is that the PHEV can be charged from the grid and also use the engine, power the electric generator and charge the battery. The PHEVs can also be driven in electric mode to higher speed up to 50 or 100 kilometers per hour and also for a longer range, again around 50, 60, 70 kilometers. The next category is the range extended electric vehicle, which is mainly a serious hybrid electric vehicle. This means that the wheels are powered only in electric mode, but that electricity can be generated by an internal combustion engine, which is coupled to a generator on board of the vehicle. So this diagonal line means that the energy source is a split between fossil fuels and electricity. The lowest ratio of electricity is used in micro hybrid electric vehicles, and the highest ratio of electricity is used in range extended electric vehicles. So in conclusion, the different levels of hybridizations are defined by how much energy comes from electricity and also if the propulsion is done with the electric machine. You can also notice that the electric vehicles have the same installed power as the plug-in hybrids. And this makes sense because a plug-in hybrid, depending on the range of the battery, can be driven as a fully electric vehicle, which means that they can have a high CO2 saving potential. On the right-hand side of the table, you can see different systems or components used for different types of hybrid and electric vehicles. In the top, we have high voltage axle drive, which is something similar to an electric drive unit. So this axle drive usually contains an inverter, an electric machine, and a transmission. For a plug-in hybrid, you can take this component and install it on the rear axle, and in the front you can have an internal combustion engine. For a full electric vehicle, you can only have one high voltage axle drive on one axle, or you can have two of these components on both front and rear axles. The high voltage power electronics usually stands for inverters or DC-DC converters. For 48 volt systems, we have a dedicated 48 belt starter generator. As I mentioned, this starter generator can generate torque and boost the overall powertrain torque, or can generate electricity and charge the 48 volt battery. For MHEVs, you also need a DC-DC converter because you want to take energy from the 48 volt and push it to the 12 volt system. For 20 volt micro hybrid system, you have a voltage stabilization system, and also you have a specific battery which allows you for deeper discharge compared to a normal internal combustion engine vehicle. In conclusion, an electric vehicle is a vehicle powered by at least one electric machine, which is using energy stored only in rechargeable batteries.